welcome back. In the last video, you saw back propagation through time, which we called BPTT. We also found out how to write the loss function. Now, in this video, we will see that what issues come out of defining the loss function this way and what issues come out of trying to do back propagation through time with a constant w. Okay, remember that the basic issue because of which we had to do back propagation through time was because u, v, w, our matrices were constants across time, because of which you had sort of recursive expressions for the loss with respect to w and the loss with respect to u. Okay. In this video, I will tell you what the two issues are which come up. Okay, so, the two main issues that come up is gradient calculations either explode or vanish. Okay. So, now both of these can happen, both of these are not ideal. Okay. Now, the other thing is the gradient calculations are expensive. You will see that each of these issues has a different solution. The solution for exploding gradients is something called gradient clipping. The solution for vanishing gradients is alternative architectures. Specifically, in the next few videos, not this one, we will see two alternate architectures called GRU and LSTM. As I had said earlier, you should see them as optional methods for RNNs, just like you had specific architectures in CNNs such as LNet, AlexNet, etc. Okay. So, and finally, for expensive gradient calculations or expensive back propagation, we have something called truncated back propagation through time. T stands for truncated. So, these are the three issues that we will be looking at within this video, or at least we will see the origins of this, and I will give you a brief introduction to truncated back propagation through time. Now, all of these are within the context of you getting a flavor of how all RNNs differ from ANNs and CNNs. There are, of course, like everything else in this course, there are a lot of details within this which we will not be able to cover within this course. This is basically an overview course, and we will try to give you an overview of this so that you can understand some issues when they come up when you try to train RNNs. So, let us look at a typical RNN with, let us say this is the time axis. As before, this is the input, this is the hidden layer, this is the hidden layer and this is the output, and let us say this is x1, h1, y1 hat, then this is L1, this is y2 hat, this is L2, so on and so forth. Let us say if this is yt hat, this is LT, and we sum all these up as we saw in the previous video. Sigma of LT from t equal to 1 to capital T is our total loss. Okay. For gradient calculations, remember when we do something like W matrix is W minus alpha times del L del W, if you are doing simple gradient descent, this term has to be calculated as sigma of LT Further, we saw that you cannot simply calculate, let us say if I have L3, I cannot simply calculate del L3 del W in the usual way, it involves something like del H3 del W, and we saw that del H3 del W in turn involves del H2 del W, which involves del H1 del W. Okay. We saw that this is true for del L3 del U also. Okay. This is basically what we called back propagation through time, because none of these terms is independent. Now, this kind of dependency creates several problems. So, let us look at a heuristic description. Okay. I want to point this out, this is not exact or rigorous mathematics, but this is heuristic. Heuristic means rough. Okay. So, it is sort of a hand waving argument. It does go through mathematically also, but that is well beyond the scope of this course. So, we will just give you an intuition for why this kind of thing causes a problem. Okay. Now, note that when you have something like Ht, our general expression was Ht is tan h of W times Ht minus 1 plus U times Xt. Okay. Now, I am going to say a few things. So, please notice this. This goes approximately, assume that you can somehow ignore Xt. You cannot, but let us say for now that you can ignore it. Okay. So, then this goes as tan h of Wht minus 1. Okay. Let me further ignore this tan h, then I will say Ht goes as Wht minus 1. What does this goes as mean? Order of magnitude. Okay. So, you are trying to guess how much is Ht affected by Ht minus 1. So, you can see that Ht scales as W times Ht minus 1. Now, long ago in week 1 we saw ideas of something called eigenvalues, eigenvectors, etc. Now, I am going to make a further approximation very shortly, but please do recall that. So, if Ht is W times Ht minus 1, then Ht plus 1 would be, let us say W square times Ht minus 1. Why? This will go as W of Ht, which goes as W square of Ht minus 1. Okay. So, in general H t plus 1 n will go as W power n plus 1 times Ht minus 1, or just to be clear I will use this as W power n Ht. So, the weight matrix as you go through time, okay. So, the weight matrix keeps on constantly multiplying. So, H3 would be so called W square times H1, and if I have let us say something like H5, that will be W power 4 times H1, so on and so forth. Okay. Now, suppose again all these are heuristic arguments, but it turns out that these are remarkably good approximations. Unfortunately, I can't show you this within the scope of this course. So, but if I have norm of Ht plus n, okay, notice Ht is a vector, remember H is simply a vector, but if I take its norm, which norm? Let us say 2 norm, okay, it does not matter which norm it is, it will be some factor times norm of Ht. Remember, norm is a scalar. So, this is a number you are trying to find out the size of Ht plus n, that will be some number times Ht, and it turns out that it scales approximately as the eigenvalues of W to the power n. Another way to see this is to assume that W is diagonal. If W is diagonal, all it will have, W power n will simply be all its eigenvalues or all its diagonal terms to the power n. Now, which eigenvalue we will see shortly, it will either be the largest or the smallest. So, the worst case scenario is this will be the largest, the best case scenario or the smallest case scenario is if this is the smallest. Now, what all this argument, we made about 6 or 7 approximations here, but all this is supposed to show is that there is a scaling going on here. As long as I use the same W, okay, as long as I use the same W which I do for RNNs throughout time, what happens is these vectors constantly get larger in magnitude or constantly get smaller in magnitude, and like the example we took in an earlier video of the sensor case, if you have a large number of time sequences, okay, I called it layers, but you can see it as a time sequence. Okay. So, if you have a large number of time steps, this number even if it is small, for example, even if it adds to 1.01, over time it is going to get to be a huge number. This is the power with this is the power of the exponential function or of the power function. Okay. So, this if let me write in yellow, if lambda is greater than 1 or mod of lambda is greater than 1, then as n increases, norm of ht plus n tends to infinity. Okay. Tends to infinity means more appropriately becomes very large. Okay. All this remember is simply heuristic. Okay. Similarly, if lambda is less than 1, this means as n increases, norm of ht plus n actually tends to 0. Now, this is simply for h. You can show that, and I would request you to try this out by looking at the expressions in BPTT. The similar arguments hold true for del w also. Okay. That is to say, if you remember, if I looked at del L3 del w, the expression in the last video, this depended on del H3 del w, and if you look up the expression, del H3 del w will look something like w times del H2 del w. Okay. There will be other terms there, but this will be a primary term that is sitting there. Okay. You will have sigma prime etc., but it depends this way. So, in that sense, this is very similar to this relationship, except it is backwards in time. Okay. So, if I look at the gradient of this, this will be w times the gradient of this, so on and so forth. So, if you back propagate in time, you are going to get a similar exponential effect there too. So, this case of either the gradient growing, if you have something like del w increasing or tending to infinity, this is called a exploding gradient. And why is this gradient exploding? Simply because the same operation repeated continuously, okay, back and back in time can actually lead to large numbers. Similarly, del L del w tending to 0 is called a vanishing gradient. Okay. Now, why are these problems? These are problems because obviously you are never going to get exactly infinity because you are still dealing with finite numbers, but recall our discussion in week 3, we have finite precision. If you have finite precision and you have numbers that are growing ever larger, at some point you are going to, in some sense, if you actually did the calculation by hand, you will have a large gradient and you will move to an entirely different space if you could actually calculate it. But the problem is, the moment it goes above the largest number that your machine can calculate, it will actually show you nan, not a number, or it will show you infinity, so on and so forth. So, really speaking, finite precision machines cannot handle exploding gradients. Similarly, you will never actually go to 0. If you do like 0.99 power 1000, it will be a very small number, but the problem is it might actually become smaller than 10 power minus 16, which is the smallest number that you can represent accurately. So, at that point you will no longer train. Okay. So, that will be called saturation, as we have said several times before. Okay. So, you will get a very small gradient and that is practically gone. Okay. There is another problem which sits here, which I will not discuss in detail, but you notice this tan h, even this tan h is being repeated multiple times. Okay. So, you have ht is tan h of w ht minus 1, ht plus 1 will be tan h of ht. So, you have tan h square. Similarly, you will have tan h cube. Now, remember, tan h itself looks like this, tan h square will look like this, tan h cube will look even flatter, and if you take tan h power 100, it will look even smaller. And notice, in all these cases gradients become flatter and flatter and flatter and they become very small. Now, all these problems put together lead to these two issues. The tan h repeated tan h problem will lead only to the vanishing gradient issue, but large number of layers can either lead to exploding gradient or it can lead to vanishing gradient. Both of these make training very difficult. Why does this make it training very difficult? Because we train through gradients, that is really how we train. Okay. So, because we train through gradients, either an exploding gradient or a vanishing gradient is a problem. Okay. Now, how do we handle this? As I have said before, if I look at exploding gradient, it turns out that a very sort of simple hack works really well. This trick is called gradient clipping. This is sort of a numerical hack. It is very simple. We decide on a maximum allowable gradient size. What do I mean by value of gradient? Again remember, gradient is a vector, so you can't give it a value, you can however give a value to norm of gradient. So, let us say we are dealing with del L del W, let me call it G vector. So, I will say that maximum value allowable of G vector is some G max. You will decide it, okay. You decide on what you are comfortable with. Just like our cutoff criterion, this is an arbitrary criterion set by you, it is sort of an engineering solution to the problem. Okay. So, how does your algorithm look? So, you are doing gradient descent, let us say. While doing gradient descent, you calculate G. Okay. Remember, G is del L del W, it could be del L del U also similarly for all the values. Now, suppose you find out, you calculate norm of G, if norm of G is less than G max, you proceed as usual. If not, then what do? We hold on to the gradient direction, we define a new gradient which is equal to the old gradient What does this do? Remember, this is simply the unit vector in that direction and you multiply it by G max. So, what this says is my new gradient is in the same direction as the gradient you calculated, but I am cutting down its size. So, if it was this big and suppose my maximum length allowed was this, I will keep this as my new G vector, just for clarity I will call it G star, okay, if this was original G vector. So, this is gradient clipping, and then of course, you proceed with this new gradient, and each time you hit above a particular gradient. Now, this might seem like a simple hack, but actually it tends to work well. So, this is what we do for exploding gradients. Now, what do we do for vanishing gradients? Unfortunately, no such simple solution exists. So, for a vanishing gradient, we use different architectures. I will talk about the basic idea of these architectures and why they work in the next video, but two such architectures are what are called the gated recurrent unit and long short term memory. You might remember long short term memory from what we actually used in the example problem in the earlier video, okay, on sensors, etc. Okay. So, that is what we use, and we will see how to do that in the next video. Now, finally, there was a third problem, which was computation of the gradient. This is expensive, as well as the solution I am going to give right now kind of handles to a certain extent both the vanishing gradient and the exploding gradient problem. So, it is sort of a compound solution. So, if we go back here to this, let us say that this figure actually represents thousands and thousands of time steps, okay, and you want to calculate back propagation through time. Now, how would you do it? The way you would usually do it is you will forward propagate through the whole thing, calculate the whole of LT, and then you will back propagate through the whole thing. Now, remember the example that we had before this, that example had 65,000 time sequences, okay. Now, would you go back for the full thing and come back through the full thing? By that time almost any correction you give will lead to vanishing or exploding gradient problems, plus it would be computationally very expensive just to do one gradient update. Now, similar to the thing that we had between gradient descent and stochastic gradient descent, you can do something similar with back propagation through time, and that is called truncated back propagation through time. Okay. So, the solution to that is truncated back propagation through time. Now, it is a very simple solution. So, let us say I am just going to draw boxes here, each box represents an input, hidden layer and output. So, let us say input, hidden layer, output and of course loss, okay, so on and so forth. So, let me just draw it at the end here. Now, given the sort of time invariant nature of RNNs, okay, remember that we are assuming that the relationship is the same, and in fact you can cut it anywhere in the middle and you are going to get exactly the same W. Okay. Given that, the basic idea that people found out is, instead of training for the whole sequence that you have available to you, you sort of split it up into many mini batches. You might recall something called mini batch gradient descent. This is somewhat similar, there are minor differences, but in notion this is very similar, truncated back propagation through time. So, what do we do? Let us say, just as an example to see here, I will forward propagate through 2 steps, okay, and back propagate through 2 steps. This is one possibility. If I do that, remember the W is the same everywhere. So, I will get some new updated W. Okay. Then I start here, forward propagate through 2 steps, back propagate through 2 steps, my W is now updated. Okay. Now, when the W is updated, I will forward propagate through the whole thing. Okay. So, I keep on doing this. Okay. Now, in general, what you do is forward propagate through K1 steps and back prop through K2 steps. Okay. The basic idea, okay, so there are many implementation details here. Luckily, most packages take care of this for us. So, this is just for you to get a notion of how all you can train, okay, so that in case you make up a new architecture, you can think of all these variety of ideas. All you are doing is forward propagating through part of the data, back propagating through a different part of the data. How does this help? If you back propagate through a small amount of data, your gradient will neither blow up nor will it vanish. Now, what is a good rule of thumb? It is actually hard to say. For some problems 100 steps are good, for some problems 10, 20 steps are good, etc. This depends on the type of the problem and you will have to experiment with it like everything else. In some sense, a lot of neural networks is still engineering, it has not yet come to the level of science as yet. So, this basic idea is called truncated back propagation through time. A simple warning, as of as of right now, Keras, as I understand it, has K1 equal to K2. Okay. So, that is, you have to forward propagate and back propagate through the same number of steps for truncated back propagation through time. So, as a summary, when you have RNNs, they actually have a strong problem. All neural networks and all CNNs, in fact, this has been the major thing that has kept them back for a long time, is they have a problem with training. It is not just the size of the data set, but sometimes either gradients explode or they vanish. This happens in everything, but it happens particularly RNNs because you have the same W across time. Okay. Because of that, you can either get vanishing gradient very quickly or you can get exploding gradient very quickly. You can also get a large amount of computation, especially if your data size is large, for the kind of examples that I showed you earlier. In the case of exploding gradient, use gradient clipping. In the case of vanishing gradient, try and use alternate architectures, which I will start from the next video, and in case of handling computational issues, try and use back propagation, truncated back propagation through time. Thank you.